Okay, let's go for it. My bad. Let me.
Okay, I'll limit myself to 3 total outbursts.
Okay. Okay. What's up, everybody? Name's Talon Frazier. People back home call me T Frey.
No, they do not.
Okay. Well, some people back home do that. And for my lab 5 for physics 2211, guys, congratulations, we made it to the end. But it's going to be Felix Baumgartner and his free fall in which he broke the speed of light. I'm just joking with you. Speed of sound. Okay, a little introduction about the lab. So we made a model that kind of modeled the motion of a human falling from the stratosphere. With it being from the stratosphere and not starting on Earth, we were trying to predict the motion through a non-uniform atmosphere. Non-uniform means not the same. I didn't know that on the last test, and I got a question wrong because of it.
That's why you're not passing.
Okay, sorry about him. But that, yeah, not the same. And we're going to determine if the speed of sound can be reached by a human. And this entire kind of lab experiment uses a bunch of different principles, but a few of them are Newton's second law, gravity, drag, and an atmospheric model. So yeah, a little preview of it. Bro ended up hitting 349.17 meters per second, which is like pretty fast because the speed of sound is 343 meters per second. So this does show that Felix actually did break the sound barrier, and he was able to do that. And the physics model predicts the real-world motion as he goes from the stratosphere, breaks the sound barrier as shown in this image, and then gets into the Earth's atmosphere. Okay, some systems and conditions. So the system is going to be Felix and the equipment that he used during the free fall. The surroundings is going to be the Earth and the atmosphere of the Earth. And then just some of the conditions. Felix and all of the equipment had a mass of 110 kilograms, which is a lot. And he jumped from an initial height of 39,000 meters high with no initial velocity whatsoever. Well, no theoretical initial velocity. He was still, moving in space and stuff. So here's some of the computational steps. We set the initial conditions in the code. We defined what gravity and drag was. Then we calculated the air density versus the height. The air density is the mass over the volume. Or not? Yeah, you know what I mean. It's not that's not the equation. I just had to slide that in there. Then we found the net force acting on Felix, which would be like the gravity minus the air resistance. And then we updated velocity and updated the position over a time interval. Okay, some model details. We used GlowScript and the Euler-Cromer method. I'm not gonna lie to you. I have no clue what that is, but I think ChatGPT said it was like right. So ChatGPT wrote this code. I'll be honest with you. But the Euler-Cromer method was used, and we did it through a timestamps of 0.1 seconds. And then the loop that we show here that I wrote by myself updates the density, the drag, the velocity, and the position of good old Felix. Okay, some of the results. We saw that in the beginning, he kind of like rapidly accelerated because it was very thin air. So there was not a lot of air resistance whatsoever in the stratosphere. So he accelerated quicker there. And then he reached peak velocity at about 50 seconds. And then he slows down as the drag increases. Some sources of error. We kind of assumed a constant drag coefficient. That's not the case when we get into Earth still. There's still going to be like a little bit of varying, but as far as Earth goes, we assumed that. And that kind of has to go with the simplified atmosphere that we put here. And the temperature is also not included, which is some energy. Okay, so what does it mean? It means that the model that we had accurately can predict the motion of this guy free falling. We also figured out that the low air density means less drag. It means higher speeds. And then jumping from the stratosphere is what allows for this type of speed. If you started on Earth or like closer to Earth, he would not be able to break the speed of sound. Okay, my cat is acting up. So what if he was on Mars? So on Mars, the atmosphere is equivalent to about 1% of what it is on Earth. So it feels like almost no drag at all. And if he was in a free fall kind of motion, it would be extremely, extremely high and dangerous speeds. In conclusion, high altitude reduces drag. It allows speeds beyond terminal velocity. Air density is a key factor, and computational physics is effective. Thank you. The end.